Hello everyone, welcome to part 2 of the lecture on pairs trading using machine learning. So in this video, we're going to cover the introduction of the three algorithms, the SVM, random forest, and neural network. So let's look at the SVM first. So this is probably one of the most widely used algorithms in the pre-deep learning era, especially in the calc community because of its good performance and flexibility for both classification and the regression. So the main characteristic of the SVM algorithm is that it can map the features from its original feature space to a high dimensional feature space. And this is achieved via a kernel function. And the purpose of this mapping is that it makes it easier to find the so-called hyperplane. So this is a hyperplane that helps us to make predictions, right? In the case of classification, it helps us to separate the different classes of data. So this hyperplane is treated, so finding this hyperplane is treated as an optimization problem that it's the one that maximizes the margin between two classes. So this is a margin maximization problem. So seeking a boundary based on the principle of maximum margin often leads to a better generalization performance. And this is often one of the reasons why it performs well and also generalizes well to the test set. Because such maximum margin reduces the risk of overfitting the training data. Right, so let's look at the regression case, which we also call it the supporting factor regression. So in this case, our target, which is the spread, is a continuous variable. Right, so we are dealing with a regression task. So this hyperplane will be used as the prediction, and we're going to find hyperplane such as the plane along with its decision boundaries minimizes the margin violation. So let's visualize what is a margin violation. Again, our task is to fit hyperplane as closely as possible to the actual data, right? And our metric mostly is the sum of squared error, right? However, we cannot minimize the SSE, which is our cost function, towards 0, because this will mean that we overfit the model if the training data produces 0 error, right? So mostly we give it a buffer, which is called epsilon. So this epsilon insensitive loss means that as long as the loss is within the buffer of epsilon, then it's fine. So this is an additional hyperparameter, which is called the tolerance parameter. And this is a threshold that's user defined before we start training the model. So there are a few technical terms in SVM. Hyperplane is a decision line, right? And that's used to predict the continuous outputs in the case of regression. For points that's on either side of the hyperplane, we call them support factors. So they are usually within a certain distance, which is epsilon, and all the points are called support factors. So based on these support factors, we're able to draw two decision boundaries as our boundaries. That is both of which is epsilon away from the hyperplane. So color is just a function that maps data from some space, feature space, to another space of a different dimension, right? So this makes it easier to find our separating hyperplane. So this graph shows the different terms here. So I have this set of data sets, which is our training data. And then this is our hyperplane in the middle. So this is two-dimensional case, just as a line, right? And then based on the distance of epsilon, so this is epsilon, we're going to define two boundary lines. These are the boundary decision boundaries. And then all the points are called support factors. And we're going to minimize the margin violations. This point is a margin violation, right? It's outside the decision boundaries. And in between is a tolerance zone. So the model tolerates errors in the predictions up to a distance, up to a metric of epsilon. So this hyperparameter epsilon, of course, is a very sensitive choice, right? So it directly determines the trade-off between the complexity of the model and predictive accuracy. Specifically, a small epsilon will lead to a complex model because if epsilon is small, then the then the distance will shrink, right? So the model will try to overfit fit accurately for each point, but that would lead to a very curly curve that is mostly overfitting model. So on the other hand, a large value of epsilon will result in a simpler model because it tries to fit all the points, more points than the line is actually leading towards underfitting model. Right? However, mostly it will lead to generalization performance if properly regularized. So this is a trade-off parameter between the generalization and between the predictive accuracy and the model complexity. Right, so to identify the proper choice of epsilon, usually we use the quantization technique so that we try it for several times repeatedly and then find the epsilon that performs best on average. Right, so let's look at the random forest. So this is an ensemble model. It's a forest, as the name suggests, and it consists of many sub-models, small models, which we call trees. So for each tree, we train it on the different subsets of the data in terms of the number of rows and the number of the rows and the columns. And then the final prediction is produced by taking the average of the individual trees predictions. So this works similarly to, for example, if a CEO in a company has many consultants, which are supposed to work independently, and then the CEO just, for example, take the majority votes of the consultant's recommendations to make the final prediction. In the case of regression, we take the average. Right? So here we have the original data sets. For example, we have 1,000 data points, 10 features. Right. So the subset one, which we use to build model one, right, the decision tree one, we have 100 points. So subsample, the subset, consists of 5 features. So we randomly sample the 100 observations and also randomly sample 5 features. So we do this for each tree, so that such random sampling will likely need to data sets that are independent, right? So set one is independent with set two. So we have multiple models, and then our correlation is also less than as if we were to model them together in the original data sets. So finally, we have the neural network model. So the neural network consists of multiple interconnected nodes, right? So they live in the individual layers. So each neuron is a function that performs a specific set of calculations. Right? So it takes the input from the previous layer, then performs a nonlinear transformation, and then sends the output to the next layer. Each neuron has a set of weights, right, which we also call them parameters of the network. So the training a neural network essentially means that's fine-tuning the weights such that the prediction is accurate and the model generalizes well to the test set. So let's look at the basic fundamental units of a neural network. which is called perceptron. So a perceptron is a single neuron that completes 2 steps of calculations, which are the weighted sum and the nonlinear transformation. Right. So specifically, if we have the input x, right, so the weighted sum will be like this. So each component, each feature will multiply a corresponding weight and sum together. And then sum together. So so this is our dimension of the features for each layer. And then we would add another term which is called a bias, right? So which we call intercept of the bias. This serves as a global shift to the weighted sum. And then finally, we would use the so-called activation function to apply the nonlinear transformation to the weighted sum. Right? So this is just a sequence of mathematical operations. So here we visualize the operations. So we have x1 to xb as our features. When they enter into the perceptron, each feature will multiply with their corresponding weights, right? So that's sum together. So we have an additional bias here. It's going to multiply by 1 because this essentially serves as the column of ones that we added manually. But in this case, the most frameworks will do it for us, right? So this weighted sum, and then we would apply an activation function phi to get the output. So ReLU, which is the rectified linear unit, is the most popular choice of activation function because it's the gradient calculation is fast. So because in neural network, we need to use the gradients to fine-tune the weights in the optimization loop and calculating the gradients for each feature, right? And it's if it's done fast, then it makes the training of the neural network fast. So specifically, and also it introduces the so-called non-linearity in the whole process, right? So specifically, it's just a thresholding function. So if it's above a certain threshold, right, then it's the value as it is, so itself. Then if it's below the threshold, then we would mute it. So it would output 0. So it outputs 0 if it's below some threshold, right? So if we train them together, then they will become a series of linear functions stacked together on top of each other. And the reason why it's popular, again, remains the most popular choice, and also there are some variants, mainly because of the fast gradient computation, as well as the non-linearity introduced in the operation. So for example, here we have the single perceptron summarized in the form of weighted sum plus the intercept that apply the non-linearity to get the output. So this is to break it down, weighted sum, and then apply the ReLU function, which looks mathematically like this, right? So this is very much similar to our appeal function for the call option, right? So if it's passes some threshold, then we maintain as it is, it's x itself. If it's below some threshold, which is mostly 0, then we would disable it, we will mute it, right, by setting to 0. Okay, so that's it for this video, and thanks for watching.